We will work at finishing chapter 3 today. If you recall, when we started this unit, I told you that we would put chapters 3 and 4 together to make one unit of material. So we're roughly halfway through. When we complete our work today, we'll be roughly halfway through this unit, and we'll have a test on chapters 3 and 4 when we finish up with chapter 4. All right, now you're going to have to put up with my penmanship today. There were so many symbols and so many formulas, and I knew typing it on a PowerPoint would have been really, really miserable. So hopefully you can read my writing, and the print is large enough, I think, that it should work out okay. All right. Going to talk a little bit today about the different kind of samples we have and also the population. We've been talking about standard deviation of samples for quite some time. We know that sample, the size of the sample is a letter N. The mean of the sample is written as X bar, and the way you find the mean is you're finding an average. You simply add up all of the X's and you divide by how many of them, right? The population, the size is a capital N, and this is a Greek letter. It kind of looks like a small letter U, but actually it's a Greek letter and it's pronounced mu, like what a cat does, right? So this is a Greek letter mu, looks like a small letter U. This is the symbol used for the mean of the population. You're going to see this for the rest of the course, okay? Mu. Mean of the population. You add up all the X's and divide by how many you have. Now you say, is it a big deal because I have a small letter N and a capital letter N? No, I will never penalize you if you use the capital when it should be the small and so on. But anyway, example 3.22 on page 128. 3.22 on 128 is the U.S. Women's Olympic Soccer team from way back in 2008, and it's the entire team. And you can see the chart that's given there. They have all the heights of the women's soccer players. They have the weights in kilograms of all the soccer players. This is the entire population of the women's soccer team. This is not a sample. So if you're going to do the standard deviation of the entire team, you might be curious, is it the same as doing the standard deviation of a sample? Well, we're going to find out. The little secret here is that it's not the same. All right, we know that to find a sample, small letter S is the symbol for sample. Here is the formula that I've been encouraging everybody to use. To make the chart, subtract the X values minus the X bar, square it, divide by 1 less, and then take a square root. This was called the defining formula, and I told you at the time there's another formula you can use if you really want to. It's called the calculating formula. But I think most of you made the chart and used that formula, okay? That is for a sample. All right, so what about, sorry, jumped too far ahead. If you have a population, the standard deviation for a population is a Greek letter sigma, okay? Sigma. How do you find the standard deviation for a population? You subtract the X values minus, remember that's the mean for the population. So you take the X values minus the mean, square those distances, add them all up and divide by N and take the square root. And that should sound a little bit familiar because up here we do precisely the same thing, except we divide by N minus 1. And that is the only difference. The only difference is you do the standard deviation for a population exactly the same, except you divide by N instead of N minus 1. And then you take the square root. There is also a calculating formula here, right here, that you can use this if you like, all right? But once again, until we leave chapter 3, don't do it in a calculator. Don't use the statistics in your calculator. I want to see you work it out. And like I told you before, once we get through with chapter 3, you can do it on your calculator. That's fine. Anybody that has a different calculator than what I'm used to, I'll help you get that figured out so you can do standard deviations on your calculator. But once again, Greek letter sigma, by the way, it's a small sigma. You may remember the capital sigma is this thing, okay? This is a small sigma. It just simply means you're going to find a standard deviation, okay? All right, author gives you some terminology here next. Let's talk about this. Stats for a population are called parameters. N, the number in the population, mu, the mean, and sigma, the standard deviation. Stats for a sample are simply called statistics, small letter n, x bar, and a small letter s. And once again, am I going to get bent out of shape if you don't know the difference between statistics and parameters? Probably not, okay? You're going to see some of this terminology in your homework, and I think it would be helpful for you to know it. Okay, so now we get to probably one of the most important things in all of statistic is probably being z-scores. You will spend more time doing z-tests than anything else in statistics. All right, so let's get started here. We have 5 test scores, okay? So this is, let's call this data number 1. And we've got 5 test scores. We have 73, 75, 80, 92, and 97. Let me make sure you can see that. Yep, looks pretty good. We want to find the mean and the standard deviation. Okay, so the mean, you simply add them up and divide by how many you have. So I have 73 plus 75 plus 80 plus 92 plus 97 equals, divided by 5 equals, I get 83.4. So this is the entire population of test scores. So mu is 83.4. Okay? Now, standard deviation. All right, standard deviation, we're going to do 73, 75, 80, 92, 97. The mean is 83.4 the whole way down in your chart. So the distance between these two would be 10.4. 10.4, and we need to square that. So 10.4 squared is 108.16. 83.4 minus 75 is 8.4. So 8.4 squared is 70.56. Okay, 83.4 minus 80 is 3.4. Squared is 11.56. 92 minus 83.4. See if I can do this without messing it up. Should be 8.6, I think. 8.6, 10, 12. Yeah, 8.6. So 8.6 squared is 73.96. And 97 minus 83.4, 97 minus 83 would be 14. So it's got to be 13.6. So 13.6 squared is 184.96. All right, so let's add these babies all up. Plus 73.96 plus 11.56 plus 70.56 plus 108.16 equals, you get the sum of them all, okay? You divide by not one less. It's not a sample, this is a population, so we're going to divide by 5. So we're going to divide by 5 and take the square root of that answer. And I get 9.48. So I know sigma is 9.48. Okay? Standard deviation of a population. All right, there's the first group we found everything here. Here's the second group. This is group number 2. And we have 80, 81, 81, 89, 91. Let's do the same thing. Mu, it's 161 plus That's 170 plus 91 equals, divided by 5 equals, I get 84.4. Okay? Standard deviation, here we go again. So we have 80, 81, 81, 89, 91. Mu is 84.4 the whole way down. Find the difference and square. So it would be 4.4 squared equals 19.36. 84.4 minus 81 is 3.4, right? So 3.4 squared is 11.56. Okay, same thing for that one. 89 minus 84.4, if it was just 84, it'd be 5. So it must be 4.6. 4.6 squared is 21.16. And the last one, 91 minus 84 would be 7, so it must be 6.6. Okay, so 6.6 squared is 43.56. All right, add those babies up. 21.16 plus 11.56 plus 11.56 plus 19.36 equals, we got to divide by 5 because it's the entire population, then take the square root of that answer, and I get 4.63. So sigma is 4.63. All right. Okay, so I've done that. All right. Now the question is, how can we compare these two sets of data? Okay, I mean, the means are relatively close. Relatively close. Okay, this one has a heck of a lot more spread than this one. Okay, and you can tell, look at the standard deviation. It's like almost twice what that one is, right? So how can we compare them? I mean, that's going to be a problem. Data for weight and height and all those kinds of things, data is always different. How can you compare them? Well, what we could do is talk about how many standard deviations the numbers are away from their mean. Okay, like for instance, in the first data set, how many standard deviations is 75 away from this mean? How many standard deviations? Okay, so I can find the total distance of these two. The total distance between these two would be 75 minus 83.4 is negative 8.4, right? Negative 8.4. That's not even a whole standard deviation away, okay? So how many standard deviations is 75 away from the mean? So I'm going to take 75 minus 83.4 is the negative 8.4. If you want to know, it's not even a whole one, it's a fraction away, so divide by 9.48, and I get that 75 in this first one, in data set number 1, 75 is on negative 0.89 standard deviations away from the mean. Okay? How about 97? How many standard deviations is 97 away from this mean? We can do the same thing. You can subtract. If it was just 83, that'd be a difference of 14, so it must be 13.6. Okay? So 13.6 divided by 9.48 is 1.43. So 97 is a positive 1.43 standard deviations away from the mean. Okay? Now the beauty of what I'm doing here, is no matter what your data is, you can always compare them, two sets of data, as different as these two sets are, if you look at how far away they are from their mean, how many standard deviations they are from the mean, okay? It's kind of fascinating. Notice the 75 came out to be a negative. it was not even a whole standard deviation, and the negative tells you the 75 is below the mean. Okay? The 97 is above the mean. So when I took 97 minus 83.4, it came out positive, divided by to see how many standard deviations. It's a positive of about 1.5 standard deviations above the mean. Okay? What I'm doing here is kind of similar to, let's say you have to fill your car up with gas every 400 miles. Okay? You're going to take a trip across the United States. How many times do you have to fill up your car with gas? Well, the first thing you got to do is find the total distance across the United States. And that's what I did here. I had to find the total distance between 75 and 83.4. I had to find the total distance between 97 and 83.4. So first you got to find the total distance. So let's say it's 3,000 miles across the United States. Okay? If you want to know how many times you're going to fill up with gas, if you do it every 400 miles, you'd have to divide by 400 to see how many 400s there are in there. Okay? And that's what I did then. I took 75 minus 83.4 and I divided by the 400 miles that you have to fill up. I divided by 9.48 and I didn't even get one standard deviation. This one came out to be a little further from the mean, a positive 1.43. Okay? All right. In the second data set, let's go to data set number 2. How many standard deviations is 91 away from the mean? 91 is how many standard deviations away from the mean? So if you take 91 minus 84, that would be 7. So it must be 6.6. And I divide by the standard deviation of 4.63, and I get 1.43. So 91, pardon me. And the second is 1.43 standard deviations away from the mean. Now, this is almost a goosebump moment here. This is very exciting, okay? These two sets is horribly, horribly different is what they are, okay? 91 here in the second set is the same as 97 in the first, because it is the same number of standard deviations away from the mean, all right? In other words, if you have two tests, okay, if you're taking a test that has 500 points, and if you're taking a test that has 40 points, can those tests ever be compared, the scores? Yes, they can. If you think about a student gets how many standard deviations away from the mean, you can figure out that, you know, if the mean was 30 on the 40 and on the 500 it was 400, you can figure out how many standard deviations there are from the mean. And if they're the same, the test scores are the same then in that way of looking at them. All right? So it's a beautiful way of comparing sets of data by looking at how many standard deviations they are from the mean. And here we have it. I put stars on it. Each data item is a unique number of standard deviations away from its mean mu. This is the z-score. The z-score is simply telling you how many standard deviations it is from the mean. Get that into the gray matter. You're going to need that. A positive means that the data item is bigger than the mean. A negative means that the data item is below the mean. But that's all that these scores do. Z-scores simply tell you how many standard deviations it is from the mean. How did we do it? Here's the rule. We took the data minus the mean divided by the standard deviation. You're going to be doing this for the rest of the course, okay? This is called the z-value. Your author loves big words. He calls it standardized variables. Anytime you see standardized variables, you know he's talking about z-scores, okay? All right, so let's move on. If you remember Shy Sam, when we did the Shy Sam problems, we were talking about how far the girls, he didn't want to date any girls that were smarter than what he was. And we talked about how far away from the mean that they were. Sorry about that. I just had to bring Sam back into the picture again. Okay, so let's go back to data set 2. Okay, back on data set 2, we want to find the z-score for each of these. All right, now we did 91. 91, the z-score, how many standard deviations is 1.43. All right, so I'm going to erase this. And I'm going to remember that 91, I'll write it right above it. The z-score is 1.43. Okay, now let's do each of the other ones. Okay, 89 minus 84.4. If it was just 84, it would be 5, so it must be 4.6. So I take 4.6 divided by 4.63, and I get 0.99. Okay, 0.99. Okay, it's not quite a whole standard deviation away. How about 81 minus 84.4? Now here we're not squaring anything. We're not squaring, so it's always important that you subtract in the right order. You always take your data value minus this. So 81 minus this would be a negative 3.4. Okay, so it's a negative 3.4. And we're going to divide by 4.63. I get a negative 0.73. All right, there's the z-score there. Negative 0.73 there, the z-score there. 80 minus 84.4 is negative 4.4 divided by 4.63. I get negative 0.95. There I've changed them all to z-scores. Okay? Now, this is going to get a little freaky here. Let's find the mean of the z-scores. Whoa. Let's find the mean of the z-scores. So I'm going to add these up. Okay? Plus negative 0.73 plus negative 0.73 plus 0.99 plus 1.43 equals, and I get like 0. And dividing by 5 is still going to be 0. So the mu of the z-scores will be 0. And the dirty little secret is that that always happens. Okay? The mean of z-scores of data will always work out to be 0. All right? Because you have the same number of distances positive as you do negative, because the mean is somewhat in the middle. All right? All right. Now let's find the standard deviation of the z-scores. Okay, so your data, here's your data, negative 0.95, negative 0.73, negative 0.73, 0.99, 1.43. Okay, we know our mean is 0 the whole way down. So the distance, this minus that, okay, is negative 0.95. So I have negative 0.95 is the distance, and I want to square that. So it's 0.95 squared is 0.9025. It's 0.73. Now squaring makes it positive, so I'm not worrying about the signs. It's 0.5329 squared, 0.5329, 0.99 squared. Should be close to 1.98, and 1.43 squared is 2.045. Let's add them all up, plus 0.98 plus 0.5329 plus 0.59 plus 0.9025 equals. Now, what do? When you're finding standard deviation of a population, you add them all up and you divide by not one less, that's a sample. You divide by the total number, so I'm going to divide by 5. And I get something extremely close to 1. Then I take the square root of my answer, and I get 1. Sigma of the z-values is 1. Please remember this. Okay, anytime you're working with z-values, the mean of all your z-values will always be 0. The standard deviation of your z-values will always be 1. Okay? All right. Now, does the data of set 2 obey the empirical rule? Remember the empirical rule, 68.26% of the data is within 1 standard deviation, 95.44% of the data is within 2, 99.74% is within 3. So go back up here. Here is data set 2. If you go 1 standard deviation on either side, it would be roughly like from 80 to 88. Well, good grief, 80 to 88, yeah, easily 68.20. In fact, almost all the data is within 1, okay? But almost all should be within 3, which is roughly 12 or 13. On either side of this would be like 97 to 71, easily. It's in there, okay? So remember your empirical rule. Okay, and now for the fun problems with z-scores. It is going to take you a little while to get used to this, okay? And I'll do the best to help you all I can. 3 weeks from now, you'll look back at this and laugh and say, you mean I actually struggled with this? Test is given mu is 92.5. Remember, that's the mean. Standard deviation is 2.17. Find z-scores for data items 84.1 and 98.7, right? Okay, so for 84.1, I do 84.1 minus 92.5 all over 2.17. And for 98.7, 92.5 all over 2.17, right? I'm just doing the formula. Z is x minus mu all over sigma, right? Okay, so 84.1 minus 92.5 equals, make sure you hit equals, divided by 2.17, I get negative 3.87. How about this one? Now that means 84.1, remember, is almost 4 standard deviations below the mean. Okay, let's do this one. 98.7 minus 92 equals, make sure you hit equals, divided by 2.17 equals 2.86. Okay, question, is either one of these unusually high or low? Bingo. Shouldn't 99.74% of the data be within 3 standard deviations? This is almost 4 standard deviations below the mean. Below because it's negative. 84.1 is unusually low. Okay? The thumb length of a female frog has a z-value of negative 2.25. If the population mean is 6.71 and standard deviation is 0.67, find the actual thumb length. Okay? 2 ways you can do this problem. First, you can do it using your formula, which many of you will like to do. So let's set it up in the formula. The z-value is negative 2.25 is equal to the x value, which we don't know. The mean is 6.71. Standard deviation is 0.67, right? You can cross multiply and solve for x. Okay? Do it by the formula. But the other way you can do it is if you understand what a z-value is. This z-value tells you that the actual thumb length, the data item, is 2.25 standard deviations, it's negative, below the mean. I'll say it again. This thumb length, this data item, is actually 2.25 standard deviations below the mean. So what you can simply do is take 6.71 minus, because it's below the mean, 2.25 times 0.67, and I get 5.20, and that's precisely what you'll get here if you work it out, 5.20. All right, let's go on to the next one. Okay. Set of home prices has a mean of 220,000, standard deviation 2,000. You're looking at a house that costs 219,000. The realtor states it's a remarkable value. Remarkable. It's amazing. It's a one-in-a-lifetime value. Is that true or false? Well, let's do what we did. If you know the mean, and here's the data item, this house, we can find the Z value. So let's take 219,000 minus the mean, 220,000, divided by the standard deviation of 2019, and see what happens. 219,000 minus 220,000 is just a negative 1,000. So negative 1,000 divided by 2019 is, I get a Z value of negative 1/2. Negative 1/2. That means this house is only about 1/2 a standard deviation below the mean. Is that remarkable? No. I mean, we know that 99.74% of the data should be within 3 standard deviations. 3 standard deviations would be like 6,000 below the mean. 6,000 below the mean would be 214,000. Now, if the house was 210 or 212,000, I'd say, yeah, that's remarkable. But 219, it's only 1/2 a standard deviation below. That is not remarkable. The data set has mu equal to 8, sigma is 2, assuming it is roughly bell-shaped, 68 point, there's the empirical rule, 68.26% of the data should be within what bounds? Isn't 68.26 one standard deviation below and above? One below and above, one of these below and above, would it not be from 6 to 10? Right? Go 2 below and 2 above. Okay? Are we loving this stuff or what? I mean, heck, this is wonderful. Okay. Find the Z-score for x equals 5. I guess I need those directions first up above. Sorry. Okay. Find the Z-score for x equal to 5. Z-score for x equal to 5, I'm going to do 5 minus 8 all over 2. That's negative 3 all over 2 is negative 1.5 for the Z value. How many standard deviations is 5 from the mean? It's 1.5 standard deviations below. 1.5 below, yeah? Okay. Suppose an X value has a Z of 2.61. This is just like the frog problem. How many standard deviations is, oh, well, no, it's even easier than the frog problem. How many standard deviations is X from mu? Well, the Z tells you how many standard deviations. It's 2.61 standard deviations away from the mean. So what is that X value? Okay, you would want to do 2.61 of these, take it times 2 and add it on 8. Why add it? Because it's positive. That'll make it bigger, right? If it was negative, you'd subtract it from 8. Let's go on down. Okay. A data set. Data set, mu is 83, sigma is 5.41, assume it's roughly bell-shaped. These are all the same. X equals 99.23. How many standard deviations? Do that. So I'm going to do 99.23 minus 83 all over 5.41. Here we go. 99.23 minus 83 equals, make sure you get equals, divided by 5.41. I get 3. It's exactly 3 standard deviations. This baby right here is 3 of these above that. Okay? 3 of those above that. What percent of the data should be outside of this range? Okay, let's talk about this. Here we are. The mean in the middle is 83. Okay? If I go from 72.18 up to 93.82. Let's figure this out. Let's find the distance here. Let's find out how many Z values that is away. 93.82 minus 83 equals divided by 5.41 equals, whoa, it's exactly 2. This is exactly 2 standard deviations here. Let's check this one. 72.18 minus 83 equals, divided by 5.41 equals -2. This is 2 standard deviations above, 2 below. Don't we know that when you are 2 standard deviations above and below, you have to have 95.44% of the data here? The question says, what percent of the data should be outside of that? Simply subtract that from 100%. Subtract from 100. Suppose an x value is exactly 1 standard deviation below the mean. Find the x. If it's 1 below, just subtract 1 off of it, right? Suppose an x value is 1.23 above the mean. Now, I didn't say 1.23 standard deviations. I just said 1.23 above. 1.23 above, just add 1.23. The x value of 90 has what z value? Just do your formula. 90 minus 83. 83 equals, divided by 5.41 equals 1.29. It's a little bit more than 1 1/4 standard deviations above. Okay, I'm going to put this homework, and there's the book problems, okay? The book problems are relatively easy, so I added a few extra problems, okay? Because you want to be a little challenged, for heaven's sakes. This is really super important stuff. Please contact me if you